Thank you very much for the intro. Actually, I should point out that the imperial information is not true anymore as of very recent. So I'm actually now working for a startup in Malibu doing sports betting, so quite the change. But what you're going to see today is actually part of my work. I don't claim it's going to make you better gamblers, but it just might. So it might be slightly related to what I do, or not. I'm not allowed to say. So first of all, who has heard of the term mathematical programming? Okay, few people, but most of you haven't, which is exactly what I wanted. The other thing I should point out actually is that you can find the slides and one of the packages I'll be talking about on my GitHub account. So if you want the PDF and the LaTeX sources for all this, it's all there. It's Campanella is my GitHub account, so just go there and you'll find it. So the plan is we'll start with an introduction to what mathematical programming is, and actually it goes under different names, so you'll see perhaps it will ring a bell after all. We're then going to talk about two specific types of programs that you can write, and we'll also talk about why there's an American spelled word there, so the linear and quadratic. Then we're going to go back to kind of what most of you probably know, which is regression problems, so linear regression, and another type of regression, which is called robust regression. So we're going to talk about that and actually show that those are linear and quadratic programs. And towards the end, which again might or might not be linked to gambling, there's an application to portfolio theory. Right, so to start off with mathematical programming, it is also known as optimization or mathematical optimization. It's got a number of names, but the main idea is that you have a set of choices and you have a function to evaluate them, and you want to select the best choice overall. So you have a set of alternatives, there's many names for this, and you want the best one. So to define the best, you need this function, which we call the objective function, which I denoted as f down there. And as an example, it might take some numbers, real numbers, typically more than one, typically p, say. So there's this vector x, which enters the function, and then the function does something, which we don't quite know at the moment, but it outputs a single value in output. And this is also a real number in my example. So then you start asking yourself, right, what if I wanted the x that gives me the maximum possible value for f of x, or that gave me the minimum of all possible values of f of x. So we call this the optimal x, and normally the optima are denoted by that little star. And this can be, as I said, either a minimum or a maximum, depending on the type of problem. This is actually, as we'll see a bit later in the presentation, but just to give you a taster of that, this is actually what we do in machine learning all the time. So many machine learning methods, pretty much all of them, rely on minimizing some cost function. So if you're training a linear regression, then you're minimizing the mean squared error as a function of your coefficients. So you're trying to minimize this sort of function. If you're doing a logistic regression, you're trying to minimize log loss, so that function down there to your right. If you're doing any sort of machine learning, really, you're trying to minimize cost function. Linear SVMs are included in this. Well, in this very framework I'm going to present to you later. But even neural networks are normally optimized by gradient descent, which is something that will come up in a bit. So in general, the main issue you have with functions, especially if you don't know what they look like, and all my examples will be in 2D. So there's an x, there's a y, and it's very simple to visualize. If I wanted, I could have done 3D plots, but I'm not a big fan of them. Neither should you. And of course, more than that is very difficult for us to see. So 2D it is for us. In general, the problem is that you might have multiple optima, and an optimum is simply a point, in this case when talking about minima, is simply a point where you cannot improve, so your function cannot become smaller in the vicinity of that point. So you clearly see that there's one down there, and there's another one further to your right. So some of them are local, some of them are global. The difference being that the local one has this property, you cannot move from the point without increasing the function value, and the global one has the same property, but on top of that, it's also the smallest possible value across all possible values that you have on x. So in that case, the one to the right is, of course, the local minimum, and the other one is the global minimum. So finding them can be quite complicated. Finding local optima is normally a bit simpler. Finding global optima is normally quite the challenge, but this we'll talk about later. Speaking of hardness, so how hard an optimization problem is, I've got a little exercise which I use in interviews, so might come in handy at some point. You've got 3 functions. They all get 100 parameters in input. One of them is f, our friend from earlier. That takes 100 real values, so any number from -infinity to +infinity, and it outputs also a real number. Then you have g, which is similar, but it takes 100 parameters between 0 and 1, so any possible value between 0 and 1 included. And then you have h, which is the last one, that also takes 100 parameters, but they can either be 0 or 1, so they're binary in this case. That's the main difference with g. Output is always the same, it's just a real value that you want, say, to minimize or optimize, doesn't really matter. If you just had to guess, would you say, which of the 3 functions would you say is the most difficult to optimize? Let's see who goes for f. Show me your hands, a few people. What about g? What about h? No more? Okay, a lot of indecision. It is h. And the reason for that is that whenever you have combinatorial problems where you need to decide which combination of items, so in this case it's a binary combination, so for each of the 100 parameters in input, that can be 0, 1. So then you have 2 to the power of 100 possible combinations, which is a big number. It's around 10 to the power of 30, a bit more than that. So this is a problem, because you need to try all possible combinations. If you try all of them -1, that last one might give you the actual global optimum, and you will never know. So there's no way but to enumerate effectively all of them, which takes, of course, a very long time. So there are some ways of getting out of this problem. Most of them don't work, or they give you some insurance of what the global minimum or maximum might look like, but they will probably get stuck in a local minimum. Variable selection is one of them. So whenever you're trying to select, if you have a lot of covariates, which is something I used to do in genomics, trying to get which of them among a very large set, which could be 1 million, say, of genetic variants, which have an effect on disease. So trying to just select those is quite complicated, and is exactly this issue here. So in general, if you are in the f or g case, when you have something which is not discrete, so you don't have just choices, 0, 1, binary or more than that. If you have actually a domain, so the function is allowed to vary continuously. Normally the function is differentiable. This is not always the case. Some functions are a bit strange. But you might be able to get analytical derivatives if you're good at calculus, or computers can do that for you. So you can get numerical derivation just by finite differences. And in general, this is the main idea, which is why it's in bold and italic at the same time. So gradient, the gradient, which is that kind of arrow, that's actually the directional derivative, points in the direction of the minimum or the maximum, depending where you're going. So it can be used, and it does give you an idea of the search direction. It tells your algorithms, whatever it might be, that's the direction we should follow to end up in the minimum. And if you have second derivative information, which in multiple parameters we call the Hessian matrix, then once you are at the optimum, you can use that to confirm the optimality. So you end up in that valley down there. You stop there because your gradient doesn't change. The gradient is 0 at the optimum. That arrow becomes a flat line, effectively. And then you can confirm that's indeed an optimum point or not. So the problem with that, of course, is that if you were to start a bit further to the right, you would end up in the local minimum. So that's an issue. And the many algorithms, especially if you're training big models, even neural networks nowadays, which are quite used, end up in local minima because they just follow down the gradient. So a few ways of getting out of this. One is to just restart from multiple different points, take the minimum of all the minima you have found, This is one way. When you have a lot of data, you cannot even compute the gradient for the entire data set, so you end up with stochastic gradient descent. You might include some randomness in there to try and jump. So all sorts of different ways of using gradient information. You're using this directional information given by the gradient. We're not really going to talk about this today, or about combinatorial optimization. We're going to talk about something much simpler, which are convex problems. So convexity is a beautiful, beautiful property of functions. A function is convex, like in that example, when if you draw a line that cuts it, see the function there is where it crosses the line, it's below it. That's convexity for you without formulas. And you have the same, the function can be concave. It means it's the other way around, pretty much. And this property is beautiful because it ensures that if you have a local minimum, that's also a global minimum. So there might be more than one. In strict convexity, there is a single one, which is even better, because then you can just start wherever you are in the function, slide down the gradient, and you're going to end up in your minimum. So convex functions are beautiful, beautiful to optimize. So that was F. We talked about F, which was the continuous one. We talked about H, which was the combinatorial one, was the very hard one. What about G, which is constrained? So you're not allowed to search everywhere. You can only search in between 0 and 1 for 100 parameters. It's a bit harder, so it's in between if you want, but not that much, because since it's continuous, at least in some restricted interval, some bounded interval, you can still compute derivatives in there. You can still use them to guide your search. The main thing that you need to ensure is that your search algorithm doesn't escape what we call the feasible region. So if you start following the gradient and suddenly you end up with x equal to 2, then you have escaped, and that's not good. But as I said, for today we're going to focus on something actually much simpler, which are linear and quadratic programs. And as you'll see in a second, they are convex, which means they're beautiful. It means they're very efficient solutions. We have algorithms to solve them, and we've had them for quite a while now. So we'll talk about the history of this a bit. But let's get into it. So the first type of program we're going to talk about is the linear program. And the reason, since I promised to tell you, the reason why it's called a program in American spelling is because this is has nothing to do with programming or coding, so computer code, but it has to do with what the army or the military, the US military called what we would call, I imagine, schedules. So trying to find optimal allocations of time, of resources, which of course are limited in the military, and trying to optimize some criterion. So where should you allocate your resources to maximize your effectiveness of measured in some way. So the first one, which was solved in 57 by Danzig, as we'll see later, is the linear program, and everything is linear, hence the name. So you have a function which has some coefficients, c, and then there's your x, which you're trying to optimize over, so you want to find the optimal x again, and that st stands for such that you can have some constraints. So you can have some equality constraints, you can have some inequality constraints. Normally you also allow x to be strictly positive. This is not always the case. This is what's called the canonical form. You can transform them a bit. The linear objective is convex, so it's very simple, and I have an example to explain this to you with kind of intuition. And this means your result of your optimization will be your global maximum, but in two cases. The first case is if you have constraints which are not consistent with each other. If one constraint says x should be greater than 2, the other one says it should be less than 1, then of course there's no solution. Or sometimes the feasible region is unbounded, as we'll see this in the example. So that's the example for you. It's just a simple function. It doesn't really mean anything. There's many examples in, for instance, a famous one called the diet problem, where you're trying to maximize your nutrient intake from different foods. So in this example, you have 3 constraints that define that triangle there, and the objective function I'm showing you in red, so for different values, for different increasing values. And the maximum, cannot reach, maybe this will work, yeah, there you go. That's your maximum right there. So interestingly enough, it's at one of the corners of this triangle, and this is generally the case for linear programs. And as you can see, so these define these three constraints define the feasible region. So everything we look at is inside this gray triangle. We can also imagine that we didn't have this constraint, then we could keep on increasing the value of a linear function, and in that case the problem would be unbounded. So that's your solution there. Not going to go into an awful lot of detail on how you get to that solution, but the important thing to know is that there are two main classes of algorithms that can be used to solve this. So if you have a problem of that form where everything is linear, both your function and your constraints, then you can use the Simplex algorithms that was proposed by Dancing in 57, or you can use the interior point methods, which were proposed kind of, I think, around 20 years later. So the performance is generally very similar. It might be very different for different problems. So the Simplex algorithm, which is actually very simple, all it does is explore all your points there. So it just explores every point of intersection of your feasible region, which, if you imagine in 2D, is some sort of polygon. In multiple dimensions, it becomes, first of all, a solid in 3D, and then something, again, which we cannot quite see. It just explores all the different corners, of which there are plenty. So in general, the algorithm is not theoretically very efficient, but in practice it is. It is incredibly efficient. So you can solve very big problems with thousands of variables very quickly. And the same goes for interior point methods, which instead travel inside this region, hence the name interior point. So that's our first example. Then we come to a second one, which is the quadratic program. The quadratic program is pretty much the same. It's just an extension, if you want, of linear programs once we start incorporating kind of x squared, if you want, information, or all cross products between the variables in our problem. So don't mind the half, doesn't really matter. But we have this form, so you have this matrix Q, we're going to talk about in a second, and then you have your x vector that multiplies it to the right and to the left. So that gives you your quadratic form. This is kind of your x squared, if you want, plus all the cross products. And then you can also have, of course, a linear part to this. So if this is really an extension to the main linear program, it's just adding more flexibility by having a quadratic objective and possibly some quadratic constraints, which is what I denoted with this strange less than looking symbol. The problem now is that you cannot simply put any matrix Q in there and hope that it's going to be convex, because that's not the case. So in general, quadratic objectives are not convex, or not always. For this to be the case, Q must be positive semi-definite. There's a positive missing here, sorry about that. So it must have certain properties to ensure that there is one solution and that you can converge to that efficiently. If that's not the case, then many solvers will just give up on the problem. Of course, there are other ways of trying to optimize non-convex functions, some of which rely on gradient information, as I was saying earlier. But there are many, many methods to solve this, perhaps less efficient than linear programs, but still very, very efficient. Interior point methods can be used for quadratic programs as well. The idea is that, again, you have some search space or some feasible region which is now quadratic. It's not linear anymore, so it's not just a solid in 3D. It's some weird shaped volume, and you can travel inside this till you reach the optimum of your function. So that's, in general, the idea of all these methods. If you're doing this in Python, there are many libraries you can use. There's one called Pulp. The one thing I should mention, actually, is that in general, all linear programming and quadratic programming, or indeed maximization or minimization software, actually, even if it's in Python, so they might have a very nice Python interface, but more often than not, it just calls some Fortran or C libraries that were written normally 40 years ago. So sometimes it's a bit awkward to make it work, but a lot of work has gone in quite recent times to get Pulp, which uses a library called CLP, though mask.clp is written in C++, so it's completely masked for you by Pulp. Google has released a big toolbox, actually, that allows you to do much more than just linear programming, and that they call their optimization tools or operations research tools. So definitely look into that. Very interesting research going on there. And Jos Ruli has also created this very thin wrapper around the CLP library in Python called CXPie or something like that. So the reason for that was that both Google optimization tools and Pulp are very high level. If you're trying to define the problem just in terms of the matrices, which is what I was trying to show you earlier, so if you're just trying to, say, define somewhere else in your code your Q matrix and your C vector and your A matrix, etc., then this is quite complicated to do just in Pulp. That's very good if you're just programming yourself, so building up the problem constraint by constraint. If you're doing all the heavy maths somewhere else and just want to call the solver, then that's quite complicated, hence the existence of this. If you're doing quadratic programming instead, there's two excellent libraries that are kind of build one on the other, CVXOpt and CVXPie. CVXOpt is somewhat similar to CLPie, meaning that you need to define all your matrices, you need to do everything yourself and pass the matrices to the solver, which will then get you the solution. CVXPie is similar to Pulp and the optimization tools from Google in that it's a very high-level interface. So you write almost like you would write on a piece of paper, so you would write some maths, code it in, this is then translated to the matrix form for you, pass to the solver, and then you get the solution back. So it's all kind of very high level, and you don't see much of the NumPy arrays that are used in the background. Right. So those are the two forms, main forms for linear problems or linear programs rather, and quadratic programs. Now the magic happens in the third part, where we actually see that those very weird looking things are actually what we've been doing all along. And normally, especially when we talk about linear regression, we don't really think about how it's optimized. There are many, many ways of doing so, and many ways that the packages we use internally solve the linear regression problem. I'm going to show you one, which is not the most commonly used one, but the reason for that, or the reason why I'm showing you it, rather, is that you can then add more on top of it. So certain things you cannot possibly do with other methods. So we start with linear regression, as I said, and linear regression is also called least squares, which is a bit of a misnomer, but you have your sum of residuals. So this is your prediction for your outcome, y, which in this case I call b, and what the outcome was. So this is your sum of residuals. If you write it in matrix form, then you have a matrix A, which is your data. This is normally called X. I've changed the notation to keep you on your toes. You have X, which is what you normally call beta. So these are your regression coefficients. And then you have B, which is what you normally call Y, and that's your response variable. So this is an approximation, if you want, of B using a combination of columns in A. Now, if you take this, you can rewrite that. You just expand that square, and this is the usual formula for expanding a square, a squared quantity, or a squared difference rather. The only difference is that now you have matrices, but what you can see here, this is your X multiplying rather this code. So this was our Q matrix in the previous slide. This is your X squared term, this is your X term, and this is your nothing term, your intercept if you want. So now we've turned this problem into a problem which is quadratic by the looks of it. These are all defined, so A is given, B is given, so all these quantities are given to us. As an aside, if you want to recover the normal equations solution, which is how this is normally solved, so this is how we normally get to X, using some sort of decomposition of the matrices and then to get that inverse. You can also set the gradient of that function, which I have written down there, to 0 and see that this actually works. So the two methods are exactly equivalent. It's just a matter of which one performs better. And normally this doesn't perform better. So the question is, why are you showing us how to do this? We'll get there. One reason why I'm showing you this is that then adding penalization to this, so adding a penalty term like this, which would be a rich regularization, so where you sum up, you have your penalty lambda, and then you sum up your regression coefficients, which in this case I call x squared, is very, very simple. You just add it to the function, do the same trick that I showed you before, you just expand all the squares, and this is what it looks like. So it's exactly the same what we had before. Now on the diagonal, which is that I, you have your strength of that regularization lambda. By changing lambda as usual, by cross-validation or what have you, you can find then the optimal value for that. So in this kind of framework, it becomes immediately obvious how to add this into the problem and how to just solve it. And incidentally, this is also a very good trick. Lambda could be very small. If you have some numerical problems, of course, matrices in regression, you always have collinearity, even though we normally assume we don't. This can fix it quite nicely, just with a little regularization there. But the real reason is that suddenly now you can do things which with normal linear regression models that you might have used in stats model or scikit-learn or in R, you cannot do. So say that you know that the regression coefficients must be positive because they represent rates, for instance, or maybe they represent intensities or something. So if you know that x should be strictly positive or just positive, or non-negative rather, then this can be very easily added to the quadratic program, and the solver will take care of that. Similarly, if you have bounds, if you know that your regression coefficients should be between something and something else, then this can also be very easily encoded there. The last one, which is perhaps the most interesting one from what comes later, is that you can also represent probability distributions. So if you know that your x should be positive and that the sum of all your regression coefficients should be 1, which is a very particular type of scenario where you have proportions, for instance, when you have a probability distribution that you're trying to estimate. And you know that in a probability distribution, something must always happen, so it must sum to 1. So all this can be very easily encoded in this framework. You just add that constraint to your problem. But now the question might come, and if you have ever done linear regression, you might have asked yourself the very same: why do we minimize the squared residuals? And this is something that perhaps we assume all the time. One reason is that the solution is good in a sense, in a mathematical sense. It is good because it's stable. It's quite difficult to change it even if you perturb your x slightly. It's unique, which is also quite important. You don't want to have multiple solutions. And perhaps less importantly now, it's analytical, meaning that you do not need any numerical methods, which normally means you don't need computers to solve it. And in fact, linear regression has been around for quite some time now. But as I'm sure you all know, if you've seen Anscombe quartet, it's not very robust. So you might have points in a line and then an outlier somewhere, and that single outlier will skew the regression line completely. So that is a big problem. And getting around this is also a big problem, which possibly trying to save a very good and simple algorithm makes it very complicated and cumbersome. So why should you minimize the square residuals in the first place? Can you think of another type of residual or another transformation of residuals which you would rather minimize? Probably. We could, yeah. You could minimize absolute residuals. Why not? And surprisingly enough, that predates least squares by around 50 years. So there was that guy Boscovich, Czech, I think, mathematician, who around 50 years before Gauss proposed to minimize the absolute deviation, so the absolute residuals, instead of the squares. And Laplace said, yeah, I think that's a great idea around 30 years later, but then another 20 years passed, and Legendre and Gauss came around, and they were big fans of squared residuals instead, so that's what won eventually. So this is where we are now. But least absolute deviation still exists. It's still very much used. It's robust, meaning that if you have outliers, it's much more resilient to that. You can actually show that least square corresponds to a kind of conditional mean prediction, whereas least absolute deviation corresponds to a median or conditional median prediction. The one problem with this is that there could be multiple solutions to this, which is something to be aware of. The other problem, which I didn't list here because it's not really a problem in this day and age, is the fact that you might, or well, you surely will have to resort to numerical methods to find a solution. So there's no simple normal equation type of thing to find a solution to this problem. But again, we have computers, so we don't mind. So that's your LAD, least absolute deviations problem. So now instead of the square, I have the absolute value, and this is the same. Of course, the norm is different. And if you look at this, then there's a problem. And the problem is that the absolute value function, which looks like a v, is not differentiable at 0. That's one problem, and it's also not linear. So it is almost linear. It's linear in the negative part, and it's linear in the positive part. But then where they meet in the center at 0, that's a problem. So there's a trick, or there's a couple of tricks which you can employ. What we can do is get some more variables. So instead of just having our regression coefficients x, you can get some more variables which are normally called slack variables that we don't really care about them. I call them t here. And you can sum them up and decide that your residuals should be bounded between these two. So effectively, this part tries to minimize t, which means it tries to squeeze this, which is the residual, more and more and more. So it does exactly what we want it to do. You can also rewrite this in another way, which is more useful, as you'll see in a second, which is as a sum of two parts. So what I can do is take the positive deviation from my residual to t. I can take the negative deviation from my residual to minus t, and then I can decompose this into two parts, which I call u and v. So in this case, you get my prediction plus the positive deviation minus the negative deviation equals whatever my response variable is. And my deviations are positive, because of course these ensure that then this minus v will be negative, so it will be my negative deviation. So in this way, we have transformed something which didn't look very linear, but almost, into a linear program. And this will do your robust regression, trying to predict the median rather than the mean, or your least absolute deviations problem. These are all the same, pretty much. But then you might ask, well, the median is a percentile, or it's a quantile. Why can I not do, or why can I not think of a regression problem where actually I'm predicting the first quartile, or I'm predicting the third quartile, so a kind of 75% percentile? And that's indeed possible. So you can very quickly expand this to create all sorts of regression lines. This is a typical problem where least square fails. See, the variance of the points increases, which is something least square is not very accustomed to or familiar with. And in this case, I can generate, these are all the quantiles from 10% to 90% in increments of 10. So I can have my line in the middle. This one is the median. And I can generate all possible regression lines for all quantiles. And the way to do this is just by introducing a simple weight, which I call tau in there, which skews the problem. So you can immediately see if tau is 0.5, which is the median, it disappears from here and from there. It just multiplies everything, so it doesn't really matter. And in this way, it goes away completely. So that recovers our previous result from there, which is also the reason why it's perhaps more intuitive to write it down like that rather than like this. And that gives you again, as I said, the entire quantile regression problem. Now, let's apply them to something. Of course, you can do all of this in robust regression is perhaps not so common. There's a very good R package. Actually, there's not so much in Python. The stats model is trying to implement this, at least quantile regression without constraints. If you use R, then the Quadratic package, which was written by one of the guys behind this entire theory, is actually very good. It implements many, many different methods with constraints, without constraints, so definitely check that out. So the example we have is from portfolio theory, and the idea is that you have, whoops, that should say B, sorry, copy paste fails. So you have two assets. They're both the same, but they're not called the same. So one is equally likely to go up 20% or down 10% in a year. The other one does the same. And then you should also assume that they're perfectly inversely correlated. So in a year when A goes up 20%, B goes down 10%, and the other way around. So they kind of track each other inversely perfectly. And this is assuming that all of these you know from previous historical information, of course. If you had this, how would you allocate your money? Would you get A, B, some combination of the two? If so, in which ratio? The main thing, of course, is to remember that they are correlated. So if you take one, maybe you should also take the other. Sorry? Yes, exactly. So if you decide to have both, then you're hedging your risk. And because they are perfectly inversely correlated, which of course never happens in real life, then if you take half of one, half of the other, then your portfolio will go up 5% every year. And there is no risk involved with this. Of course, this is the world of theoretical finance, which is very different from actual finance. So in general, the model that's used, and it's not the only one, as you'll see in a second, is this mean variance approach of Markowitz, for which he won the Nobel Prize many years ago now. So you have historical data, returns on investments. You know how your assets or your shares or whatever it is you're trying to put into a portfolio did in the past, and that's this R. And you have many time points which represent days, months, weeks, whatever. So you have your reward, and historically the reward is just the mean. So how did it do in the last however many time periods? And then you have the risk. And the risk, Markowitz says, is the variance. So this, as if you recognize it, it's just the mean minus, sorry, it's just the value minus the mean squared, summed over your observation. So this is actually just the variance. So you can compute this quantity for one asset. You can then put more than one asset together and into a portfolio X and compute the same quantities. Now this is interesting because this is back now. The portfolio we assume is a distribution and it sums to 1. So you can just say, well, my capital is 1, or it's some units, so you just decide on fractions of allocation. Of course, if you have 1, where 1 could be, say, 1 million, or if you have 10 million, it doesn't really matter. The allocation is proportional to your capital. So this constraint, which we saw before for the unit sum, is actually back here in portfolio theory. Now, what you would like to do ideally is get the maximum reward possible and the minimum risk possible, which of course is impossible because you cannot minimize and maximize two things at the same time. What you can do though is solve this problem, and this problem has the reward, which again is just the mean return, and then it's got the risk, which is that variance, or is that variance covariance function when you have a portfolio. And then Markowitz says, well, let's just put this mu there, which represents the risk. So you have this parameter which is allowed to vary. If you put it to 0, then you maximize reward only. Not a good strategy unless you have very deep pockets and money to burn. If you start increasing mu, then the risk component there becomes more and more important, so you tend to become more conservative. And you can imagine kind of trying different solutions. mu equals 0, 1, 2, 3, etc., they will give you slightly different allocations. All of them are optimal in this sense, but that's always depending on some value for this mu. So from this trade-off, if you want, between the reward and the risk. So we talked about the constraints, which are linear, and it's just that the portfolio should be kind of a probability distribution, or if you want, it should be a distribution with different fractions summing up to 1. But what about the objective function? So the reward is a mean, so it's linear, and the risk is a variance, or a variance-covariance function. So it's quadratic. It turns out that it's not only quadratic, but it's convex as well. So this can be solved very efficiently using just a quadratic program. So you can get your perfect allocation of your capital on however many assets you're considering by solving a quadratic program. So you can just get your optimal x, and everything we talked about previously holds. So you have one, it's optimal, it's the only optimum, etc., etc. So there is a single solution, at least for one choice of mu. Now the question is, why should you minimize variance, or why should you think that variance is a reasonable measure of risk? And this is actually a bit problematic. So in the finance industry, people have realized this for quite a long time now. Variance-based measures like the variance that we used there, the straight variance, are not monotonic, meaning that if you put together two assets, suddenly the variance, or the risk, as we can call it, doesn't necessarily add up. So as you would expect. So some other measures have been proposed. Some are quantile-based, for instance, value at risk, but they're not subadditive. And all these properties have reasons to exist, which are outside the scope of today. But the main reason with those is that normally, if you have value at risk, which is, say, a percentile of your loss distribution, anything beyond that is ignored. So you know where your 95% of your risk is, but you know absolutely nothing, or you're not characterizing at all what that 5% that you're ignoring looks like. So that 5% occurs not very often, because it occurs in 5% of the times, but there might be a lot of millions to be lost if that occurred. So it's a low probability, but it's a very high risk. And something like value of risk ignores this completely. So the idea then was to get some coherent so-called risk measures, and this is a work by Artner. And there's a big family of those: the expected shortfall, the conditional value of risk, so C bar, or a generalization of this, which is called the alpha risk. But the interesting bit is that all of those can be solved quite elegantly as linear programs. So all of them in pretty much the same way as the Markowitz allocation are solved as linear programs rather than quadratic. And the alpha risk models are actually quantile regression problems, or combinations of quantile regression problems. So that's pretty much it. Just to recap, the take-home message, I guess the most important one, is optimization is at the core of what we do, and it's perhaps something that with all the neural networks and machine learning we forget, but it's there, it's behind a lot of the things we do. So if you're not going to become a user, it's still, I guess, quite important and quite useful and quite informative to just know what's going on. And sometimes the failure of algorithms to do what you expect is due to convergent issues, with which I battle on a daily basis. The other thing to take home is that some problems are intrinsically much more difficult than others. And this is important because if you identify that the problem you're trying to solve is one of those, then you should run, and run far away. In general, the one thing that makes a problem easy or not to solve is convexity. If it's convex, happy days. If it's not, so if it's non-convex, by convexity I mean convex or concave, doesn't really matter. You can always invert the sign. But if it's not convex, then you have local minima. You might have many local minima, in fact, meaning that your algorithm will get stuck there and your life will be generally miserable. LPs and QPs are easy. There are a lot of tools to solve them. A bit complicated perhaps in matrix form, but a lot of libraries allow you to use this higher level interface, so they actually make it quite palatable, hopefully much more than I made it today. Many different regression models are actually, or can be thought of rather. They're not necessarily solved in this way. You can think of them as linear programs or quadratic programs. And if you want to solve them like this, then you can add additional constraints on them, which makes them actually quite interesting, or more interesting than certain other algorithms. And some portfolio allocation models can also be seen as this. So you can kind of modify them, and then since it's all constraint based, you can add more constraints. You can incorporate, if you want, prior information that you have on the regression coefficients directly into your model. So that was myself. Thank you very much for your attention. And if you have any questions, please ask.
Right, straight to questions.
Yeah, thank you for the talk, first of all. In the beginning, you mentioned this three-function problem and said that the binomial one is the hardest to deal with.
Yeah.
But can it not be approximated with Poisson distribution to avoid these expensive combinatorial calculations? And on the other hand, the first one defined on R, usually this kind of function usually require to be normalized to get to the interval from 0 to 1. And then the distance in such high dimensional continuous spaces becomes increasingly harder to calculate, to deal with. So why is the latter is the most expensive then?
Some very good points. Let me go back. Where is it? There it is. So for the last one, the main issue you have is that for each of the 100 parameters, you need to pick a value which could be either 0 or 1. So you might go from 100 zeros to 99 zeros and then a 1, or all possible combinations of that. And if you know nothing of what's going on in that function, then there's no way but to try all of them. It's literally the only way you can, if you want to find the global optimum at least, there's no other way but to try all possible combinations. For the first one, you're very right that in a very big search space, then the volumes become incredibly large. So there's this kind of a problem if you're doing clustering algorithms and all that, for instance. But if you can assume, which is something I probably should add to this slide, if you can assume that the function is differentiable, then you have your gradient information that can guide you for each parameter, well, for the 100 parameters together, can guide you towards the minimum, say, or the maximum. So in that case, that doesn't become a problem.
As your topic is based on mathematical programming, you mentioned Python, which is not genuinely, it is not scientific programming or mathematical programming. Do you find Python is the top for such kind of thing? From my experience, I found Octave, for example, is very highly vectorized and accurate because it is really scientific. But the problem with the community and the update. So from your point of view, which the best scientific programming which we can really focus on or worth to learn?
Ooh, difficult question. So in terms of tools, I guess, that you can use for this, there were a few there in Python. Unfortunately, a lot, and I've seen as I've been researching libraries to do this, the problem I have actually at the moment is doing this many, many times per second. So efficiency is really a concern there. And where is my slide? There it is. Of these tools, well, as I said, I ended up writing CXPie, But all these tools, a lot of them really lack a community. So you might find the underlying code that drives most of this is incredibly old. It's normally from the 70s. And you have some wrappers written in C or in Python or what have you on top of them. So they work. They're a bit difficult to get to start working with them, but they're there. If you can afford it, then there are commercial solvers, which are incredibly expensive and much, much better. So that's the sad reality, is that in the open source community, there are some very good tools which are difficult to use, or they're not immediately accessible. I think I've not really checked out Google optimization tools. I believe that's a good library if you're trying to kind of solve it from translating the maths directly into computer code, which is perhaps similar to what you were asking. So that might work. But in general, commercial solvers, in terms of efficiency as well, are much, much better. Octave is open source, yes. Yeah. And yeah, I'm not referring to MATLAB, perhaps. I'm referring to software by IBM, like Simplex, which really solves, in the specific instance I saw, it solves the problem in a tenth of the time. But then it costs, well, infinitely more, because of course it's over divided by 0, which is free software.
Thank you very much for the talk. I have 2 questions. First is that obviously this is very good parameterization for the way like you can add lots of things, it's flexible. But if you have collinearity or if you have over-dispersion, wouldn't you actually want to transform your outcome, for example, to avoid the problem, or drop some of your covariates to sort of deal with collinearity instead of actually come up with like a regularization parameter there, or defining your problem in this framework? Have you looked at it? Would it be easier to do that instead of actually going like very mathematically deep into this? And the second question is, what will you actually do if you have a convex problem? So you said that you have to run, but are there any solutions available?
Okay. So for your first question, you can of course apply all the tricks that we normally apply. You can apply here as well, but the main difference is that in this framework, if you have any knowledge on the parameters, on the regression coefficients, I guess you can call them as well, you can incorporate that. So if you're doing your linear regression and you want to, say, have only positive regression coefficients, that's not normally possible. The algorithm will give you a solution, and then it's up to you. You might transform them. For the analysis of proportion, there are a few tricks to do that, which might be what you were referring to. So that's another solution. Yep. But in general, you cannot just impose this in the program itself or in the problem itself. So that's a different way, I guess, to look at it. If you don't have a convex program, what do you do? Tough one. You try to optimize it from multiple starting points. That's the easiest one. There are some global optimization algorithms. Just try different combinations and hope for the best. But in general, especially if you have, again, the bane of my working life at the moment, if you have multiple local optima, so if you have a function with many different points which all look roughly the same, then there is really no solution to this problem. You might explore the different optima, see whether they are any different to you. Perhaps the function is misspecified. It should be something else. So it shouldn't have that many local optima. It should actually be steeper. Sometimes changing the function form a bit helps. But if it's not convex, then optimization becomes suddenly incredibly more difficult, especially global.
Right, I think we're going to have to end it there, if only to leave some topics to discuss at the next meetup. So I'd like to thank Gianluca and all the speakers again, and indeed our sponsors and Skills Matter and CodeNode for providing the venue for this Data Science Festival. Hopefully we will see you at next year's event, but there will of course be the meetups coming in the next few months, and hopefully we'll see many of you there as well. Anyway, thank you again for all the interesting talks.